Let's look at analyzing data when we have one quantitative and one categorical variable. A quantitative and a categorical variable together would be something like this. Does owning your own car help you predict how many cars are in the family? So does knowing whether or not someone owns their own car help you predict the number of cars in the family? And the way that you would do this is you would set up into two groups the people who answer the first question a certain way, analyze their numbers, and the people who answer the first question the other way, in this case the yeses and the nos, and you would put the nos and analyze their numbers and see how their averages play out. So what we can do is we can copy and paste this all into StatKey. Now the one thing that we're going to run into is you'll find that the categorical variable has to come first when you plug it into StatKey. It's just a function of how it works in there. So I'm going to copy and paste it here so that I have my categorical one first and my quantitative second. And then I can paste all of this in together. So I'm going to recopy, Control C to copy this whole new section here that I made. And then when I go into StatKey, I am choosing one quantitative and one categorical variable. If I click on Edit Data, I can again select all my data, Control A, select all of my data, and then paste, Control V, all of my new data here. Again, no commas, it's just a tab. So I'm going to change my labels here at the top so they are each one word, so I don't want those spaces in there. So I'll do own and then number. And those aren't great labels, but we will make that work. And when I do that, it will automatically create two separate dot plots, two separate histograms, and two separate box plots for me. And what's interesting here is if someone owns their own car, this is the box plot of how many cars are in the family. If someone does not own their own car, this is the box plot. Yeah, there is some overlap here, but not very much. You can see that the middle is very shifted from this one here, the nos, all the way up to the yeses. And if you look at the mean here, the average, it looks like people who do not own their own car, their family has an average of 1.6 cars. For people who do own their own car, family has an average of 2.9 cars. So not only does that one person's car add a full car to the average, but it looks like the siblings are probably more likely to own a car if they own a car, bringing up that overall average even farther. So there's actually a pretty huge discrepancy here between the two groups. And when you see that kind of a discrepancy, you're going to go back to your original data and say, yeah, owning your own car does help you predict the number of cars in the family. In fact, knowing this allows me to make a significantly better prediction. I can add almost 1.3 cars to my guess of what it would have been if you didn't own your own car. This type of data here, the categorical and quantitative, where you're analyzing with a box plot or looking at differences in means, this is something you'll see come up in a lot of experiments. So if you have treatment group 1, treatment group 2, maybe a placebo treatment group, each treatment group would be its own set of quantitative data, and you could look at all of the box plots, histograms, and dot plots for that data stacked on top of each other and compare it. You could look at the mean for the nos and the yeses, and you could compare the mean treatment level for group 1 and group 2, things like that. So whenever you have some sort of experiment, you're often going to have those treatment groups, and each treatment group would represent one column here of numbers or one of these two graphs.